This video is going to be about two-slit interference and diffraction gratings. So remember what we did in class. We had this diffraction grating and we had our laser pointer, and when we aimed our laser pointer through the diffraction grating, we got some dots. There we go, there's your dots. Let's see if we can get them on there a little bit better. Alright, so we got some dots. We got a bright dot in the middle and we got some dots to the other side. So we want to figure out what's happening here, and we'll take you through a couple of ideas first in order to figure that out. So let's go. First, I want to talk to you about the general idea that is called diffraction. And diffraction is a phenomenon where if you take some waves, say water waves or light waves, and if you put them through a narrow opening, then once the waves go through the narrow opening, they're going to spread out after that narrow opening. So I like to say waves spread out. And that has to be a pretty narrow opening. If I have a wide opening, then the waves aren't going to spread out very much. So if I have an opening like this and I have waves going through, most of the waves are just going to go straight through. They might spread a little bit around near the edges. If I have an opening that's very narrow, then I get a lot of diffraction. So waves coming through like this, they're going to spread out in all directions like that. Waves spread out. That's diffraction. Waves spreading out. So interestingly enough, this thing is called a diffraction grating, and it uses the principle of diffraction, but it also uses the principle of interference. So let's talk about interference, and in particular we're going to talk about what we call two-slit interference. So we get a new page here, and let's talk about two-slit interference. That's not how you spell interference. Okay, we'll try it again. Interference. All right, good enough. So what's happening here? We're going to do the same thing. We're going to have light coming in, and there's going to be a boundary that's going to hit. This time the boundary is going to have two openings in it like that, two slits. A couple important things. First of all, this light on this side, we're going to start out with it as monochromatic, which means that it just has one color, and we're also going to have this light be coherent. Coherent means that all the waves are lining up with each other. So it's a little messy how I drew it. Coherent light would be more like this, coherent light. We're going to want our light coming straight at these two slits this way. And that's not the best drawing. And then we're going to have a screen over here. So here's a screen, and we're going to see what's going to happen. Now I'll show you this in class, but what we can imagine is light is going to spread out as it comes through this opening and go in lots of different directions. Light's also going to spread out as it goes through this opening and go in lots of different directions. So if I look on a screen way over here, what we'll find is that some light from this slit is going to go through and hit the screen over here, and some light is going to go through and hit the screen over there. And what we're trying to figure out is what's happening on the screen at that spot. We talked about interference a little bit, and so when we have one wave that's like this, and then another wave that's slightly off from that wave, we could get there to be a little bit of interference there. Of course, if my waves line up exactly like this, then we're going to get constructive interference. And if my waves end up like this, then we're going to get destructive interference. This right here is going to give me a bright spot, and this right here is going to give me a dark spot. So we get bright spots and dark spots. That's going to be determined by how many wavelengths of light can fit into this distance between there and there, and how many wavelengths of light can fit into this distance. And what we're going to see is, we're going to see that on this screen over here, we're going to see a series of dots going across, just like with the diffraction grating. Where there's a gap in the dots right there, that's a dark spot, so we have destructive interference, and then constructive interference, destructive interference, constructive, destructive, constructive, and so forth. So we get this series of dots as it goes across the screen. And there's an equation that'll work with this, and this is the same equation that we derived in class. And let me set up a couple of variables up here so we can understand what we're talking about. First of all, we've got the distance between the dots over here, which is going to be y. We've got the distance from the slits to the screen, which is going to be d. And then little d right here is going to be called the spacing of the slits. That's how much distance is in between the two slits right there, the spacing of the slits. And if we put this together, then the equation we figured out in class based upon our lab was y equals m lambda big D over little d. Just to remind you what this m factor is right here, this m value can be 0 or 1 or 2 or 3, or it could be -1, -2, -3, and so forth. The 0 one is going to be the dot that ends up right in the middle, and then m equals 1, m equals 2 on either side of that, m equals 1, m equals 2 on either side of that. Just want to show you, we have here an actual double slit, and let's see if I can get this close enough for you all to see inside there. It's hard for it to focus. Let's see if this is going to focus. Let's get it extra close inside there. So it's hard for you to see that there's two slits inside of here, but this was something that was sort of specially made for the school, and you can see that the spacing right here is 300 micrometers. 300 micrometers is the spacing right here. 300 micrometers is the spacing. So what we actually really need for this to work out over here, for this two slit interference to work out, is we need, let's see if I can get the focus back. That's having some trouble. There we go. We need this D value here to actually be pretty small. The wavelength of light that's coming in visible light is small, so we need this D to be pretty small. And in this example, it was 300 micrometers. That's 300 times 10 to the -6th meters. So that spacing was pretty small, and that works out to be 0.0003 meters, right? So that's pretty small inside of there. Let me draw another picture in here and get up a couple more terms and then show you a quick example as well. So let's see. We have our two slits like this. We've got this spacing right there, which we call little d. We've got our screen over here. We've got this spacing here, which we call big D. And then we've got our coherent light coming in like this. And what we see is dots on the screen over here. Dots on the screen, dots on the screen, dot, dot. There's always going to be one dot that's right in the very center right here. So if we just trace this over, this one is going to be called the central maximum. And it's going to be a bright spot. So we have the central maximum, it's going to be a bright spot. This one on this side is going to be called the first order maximum. And then this is the second order maximum. Also on this side, we have the first order and we have the second order. And it doesn't really matter which side you go. Our y distance is going to be the distance between any two maxima. So that's our y distance right there in our formula. Remember, we have y equals m lambda big D over little d. So there's our y is between those two. And then d, big D is the distance between there and there. Little d is the distance between the slits. Let's take a look at an example and work this out. Here's our example. We've got light of wavelength of 60 nanometers, falls on two slits, and the distance between the slits is 0.02 millimeters. How far is the first order maximum from the center on a screen that is 2 meters away? I'm going to need to do some calculations here in order to figure this out. So first of all, we can draw a little picture if we want to. I don't think that's totally necessary. Let's list out what we know. We know that big D is 2 meters. We know that little d is 0.02 millimeters. We know that the wavelength of light is 600 nanometers. And we're looking for the first order maximum. So our m equals 1. we need to actually get everything in the same units right here if we're going to plug something into our formula. We're going to plug something into y equals m lambda d over d. We have to have the same units for everything. And I like to use meters. For everything that I use, I like to use meters. So that's already in meters. If I've got 0.02 millimeters, the way I like to think about this is I'm just going to write it as 0.02 times 10 to the minus 3 meters. Now you could, if you wanted to, say that this is the same thing as 2 times 10 to the minus 5th meters, but that's an extra step that I don't necessarily like to take. So I just write it as 0.02 times 10 to the minus 3 meters. Same with this one. I'll write this one as 600 times 10 to the minus 9th meters. The nano is minus 9th. I could also write this as 6 times 10 to the minus 7th meters if I want to, but for me I just save myself the step and I'll just type that straight into my calculator. So as far as figuring out this problem goes, we're going to have 1 for our m, and then 600 times 10 to the negative 9th meters, big D times 2 meters, divided by my little d, which is 0.02 times 10 to the minus 3 meters, and then we just have to work this out in a calculator. So when I do this on my calculator, which of course I don't think you all can see up there, there we go, let's get that angle just right, let's clear that away. So when I do this in my calculator, I'm just going to write 600, let's see if I can get this closer to you all, 600, and then I do my times 10 by getting the e right there, so that's 600 times 10 to the negative 9th, just like that. Multiply that times 2, divided by, and I'll just write 0.02 and get this e, 0.02 times 10 to the negative 3rd. All right, I'll just type it in all like that, and here we go. So the answer is 0.06, and that's going to be in meters. All right, 0.06 meters. So that would be 6 centimeters. Distance down here, the y is going to be 0.06 meters, or if you were to write it in centimeters, that's fine, but just keep everything in meters is good. So this is a great way to do things, just like this. Okay, let's look at one more thing here, and that is these diffraction gratings, because they have a slightly different scenario. It turns out that the equation that works for them is the same, and why that's the same is a little bit different. So what's happening in this is we've got something that says 1,000 lines per millimeter on there. So you can see 1,000 lines per millimeter linear diffraction grating. If we were to zoom in and look at this diffraction grating super up close, what we would see is that there are many lines in there, all super close together, and they all have the same spacing. And it turns out that when you do an interference experiment, we had 2 slits, but if you have many slits and they all have the same spacing, you get a very similar result over here. So if this is my monochromatic light, and here's my screen over here, then you get the same thing, you get a pattern of dots. The pattern is slightly different, there's some different phenomenon that happen, but basically it's the same formula as the 2 slit, it just has more slits. So we still get y equals m lambda d over d. The issue with the diffraction gratings is figuring out this d value right here. This is the spacing between the slits. This value up here, this 1,000 lines per millimeter, is not exactly that. So we have to figure out a way to get this 1,000 lines per millimeter into a d, which is how many millimeters per line. Let's take a look at how that's going to go. We'll do it down here. So I have 1,000 lines per millimeter. What I need to do is I need to actually take the inverse of that, the reciprocal of that. So my d value, my little d, is going to be 1 over 1,000 lines per millimeter, right? And that's going to give me 1 millimeter per 1,000 lines, which is going to give me 1 times 10 to the minus 3 millimeters per line. But once again, I want to get that into terms of meters. So this is actually going to be, since that's in millimeters, that gives me an additional 10 to the minus 3 here. So this is actually going to be 1 times 10 to the minus 6th meters per line. that means that in my diffraction grating, the spacing between any of these two lines right there is 1 micrometer. 1 micrometer. So they're super, super close together. It makes sense that they're close together because you can't see them. Right? There's so many of them in there, and they're so close together that you can't actually see them. It looks like it's clear, but it's not. So that's the deal with the diffraction gratings. You have to take the lines per millimeter, or whatever the value is it gives you, and make the reciprocal of it, keeping in mind that you want your units to be meters per line. So you want this units to be meters over here. And some of the problems get a little bit harder, and some of them get a little bit easier in figuring all that out. Hopefully this is a nice intro for you. Of course, we still have a lot to deal with in terms of why and how it works, but this will at least allow you to get started on some of the homework problems. There you go. Enjoy.